seem the same. I will ask, I guess later, hopefully people will tell me whether it is, it makes any difference for people trying to listen to the recording. It's not easy. So the recording is already rolling. We'll be talking more about Gaussian distributions. There is a lot to talk about in Gaussian distributions, but the XKCD shows us one way to not to think about Gaussian distributions. Before we do that, a couple of announcements. So basically, the course schedule has been updated. Hopefully, you've all got and read the announcement on Piazza. We will have 2 in-person plus remote dual delivery lectures. One is next week, this time, when we talk about the second part of Gaussian processes. And then in 2 weeks after that, we will have a guest lecture from a local company, Penten, where David Leibowitz will talk to us about machine learning for cybersecurity, broadly construed. There is no tutorial in this week. I encourage people to attend the assignment 1 drop-in. It will be recorded if you cannot make it. It's on Friday, 5 p.m. There will be no tutorial in week 8. I hope you enjoy your quiz 2, which was just released. There are not a lot of questions, only 9 multiple choice questions. Some of them I would say you can probably do in a few minutes or just after thinking about it. Some of them will require a little bit of calculation. So video assignments are released. We are working on assignment 2 release. Hopefully that will be done soonish. You've also just got feedback for assignment 1. Take a look, and if you would like to raise any concerns about the grades, use the regrade request on Grayscope. That will direct it back to the person who graded for review and created the rubric and so on. If you do it any other way, given the size of our team, yeah, we basically cannot deal with and then pin down the person among the 15 people who are responsible and chase them to reply. Anyway, so that's the logistics. I would also like to thank those of you who have provided feedback in the anonymous Watto survey that were open just either just before or like over the teaching break. So I'm going to respond to a summary of a few frequently raised concerns. First of all, I would acknowledge the great diversity of people in this class. There are still nearly 280 students, and there's about, 16 of us teaching staff. As can be expected in such a large class, everyone's background and preferences and styles of learning are very different. I know that by me sitting here and talking to you over the material will not suit the learning style and preferences of everyone. Yeah, but tutors and a small group teaching hopefully mitigates that for a while. And also remote learning is really hard. We know all of that. We have heard, right, lots of comments about the mathematical content of this class, and this class did have a reputation of being somewhat demanding in math. I would just like to comment that, so some people commented having the background of IML. And then between IML and SML, I would say you're expected to use the, say, vector calculus and linear algebra you have practiced in IML, but the ways you use it necessarily needs a leap. So I would say that using the math that people have learned in IML and other mathematical courses in the machine learning context in SML, I would say it's one of the main skills in statistical machine learning. We do resonate that many students with a CS background would find it somewhat challenging, and we're here to help. there is, right, so the quote here is taken literally. I do gather that there might be more than one student finding the content too easy, and it does not feel challenging enough to be a 4,000 level core class and would like more difficult assessments, which might be not too far off because the assignment 1 grades are pretty high on average. For that, I would say that if the assignment grades continue to be very high across the entire class, we might have to make the final exam a bit more challenging to keep everyone entertained. And for those of you finding this class easy, you're most welcome to approach one of us, like faculty in CS for a research project or individual project. Well, okay, more seriously, a few like shared concerns. So people asked about, okay, how important are the derivations and proofs in this class? And sometimes we skip them. Either they're in the book and we skip them. Sometimes they're not in the book. I write it out, but I don't talk over that slide in detail. I'm happy to say that the expectations for derivations and proofs are, first of all, you're expected to know the important ones, such as the EML objective, Lagrangian multipliers, being able to differentiate simple matrix and vectors and find the stationary point. Beyond that, if things are skipped, it generally means that you can grasp the overall logic if you just trust that the proof is there. I sometimes write it out for you because I feel for people who would like to read the book and get to the bottom of things, it's unsatisfying to have some of it skipped. The book is very well written. I would say that it does selectively skip details, right? So I would say the things that we cover in detail is more important than the things we skipped, if that's not been obvious. I hope that helps. Another thing that we've been hearing is motivating the course material, the assignment, and so on. So while I admit that motivations tend to be mathematical in this class, for example, the difference between linear regression or linear regression with feature functions and those with kernels, and now with GP, for example, in this class, in this particular lecture. In the practical application, a lot of times you can use like a collection of any one of these tools. Like if you're doing regression, then use neural network, use linear regression with kernels, use feature functions, use a Gaussian process. But that may not be what you're asking about, right? So we're happy to help. I have been trying to sprinkle bits of motivation or basically machine learning scrutiny kind of material throughout the lecture. Some of we will try a bit more to have it written down in some slide so that people can better anchor it. Right, so there were also a comment that relate from the course rep that sometimes how assignment 1 is connected to the lecture is not super obvious. I would say so definitely do ask these questions on Piazza and tutorial, and we'll try to address it. When assignment 2 is released, we'll make sure we address that. The last point I think is worth addressing is which parts are important. So this is a good question. So I think in broad strokes, every single lecture has what I call the table of contents slide. And we usually talk over it before and after the lecture. So if that's still unclear, do ask questions. So there are, in certain lectures, there are certainly like, I guess, detailed parts or parts that has a lot of details, but we won't go into those details, which I would tell you that's maybe not so important. And the core concepts and the things that we expect you to apply is certainly important. For example, how does EM algorithm work? You have done it for the exponential family, which is a non-trivial application of an EM algorithm new model family. So that's certainly important, right? So given that, this is what we're going to talk about today. This lecture will have material from parts of the Bishop book, as well as what's called the Gaussian Process book. The book title is Gaussian Process for Machine Learning. It's written by Carl Rasmussen and Chris Williams. It's well written. It's so-called basically a classic Gaussian process book. So there are bits that are drawn from there. I will talk about why we need to draw from them as we go along. So we will first motivate Gaussian processes, define it, talk about kernel functions. So hint, it's related to regression and kernels. And then we'll talk about Gaussian process regression in some detail. And I will talk about one sampling algorithm that's presented in the GP book. And advanced spoiler is this is in your assignment too. One of the questions asks for this sampling algorithm. So that's important. Computational cost is, I would say, important. So at the end, there was, of this lecture, there's a slide about estimating hyperparameters. I would say it's good to know that you can do this, but I won't ask you to reproduce it. All right, let's dive in. So why do we care about Gaussian processes? So it's another way to sort of learn very flexible, let's say for the sake of this lecture, regression functions. Next week, we're going to look at classification. So it is in the supervised learning setting. And it is, depending on, so we've talked about the difference between parametric and non-parametric models as a term. So some would call this non-parametric model, but really depends on how you look at it. At the very beginning of this class, I shared this slide as a case study of Australian-specific application of some cool machine learning. I don't expect you to remember it because we didn't go into any detail. But after this lecture, you will be able to appreciate and understand what goes in this, right? So the problem that's being solved is geophysical inversion. And the inversion problem involves basically we can measure temperature, conductivity, density, magnetic susceptibility, and permeability, and so on. So these are inferred from things like gravity, magnetics, and seismic. So the Earth is a very complex system with some measurements. The task is to infer the underlying mechanism, physical mechanism from the observations. Right, and the method being used is Gaussian process regression. And the advantage of using Gaussian process regression here is that it naturally provides both predictive distribution over the inverted quantities and the principled method to fuse different types of observations. All right, we'll see how these claims are realized as we go through. All right, so this approach is run on South Australia data set on gravity and drill holes. I guess with a country rich in natural resources, being able to do tasks like this is obviously attractive. All right, so here is another two motivating scenarios from the Gaussian process book. The first one we'll talk about in some detail, again, when we talk about the empirical section. It is about, we can also think about this as an inversion problem, basically inverting the motion and force model of a robotic arm. So the input are X, like 7 joint positions, velocities, and accelerations for robotic arm. The output is torque, y, basically, what force you apply on each of these joints to get the robotic arm to be positioned in and move in a certain way. So again, this is another inversion problem, right? You would say, hey, I do physics. And the usual way I drive a car or I drive a machine is I apply a force and it moves. Now we know the movement. I want to recover the force. Why is this sort of not a simple physics model? Why do we need machine learning for it? The reason is, the book says that robotic arms are driven by hydraulic systems. So the interaction between the mechanical rigid parts and the hydraulic system, the fluid, is not easily described by a clean set of physics equations. The more joints it has, as you can imagine, the more interactions and complexities you have. So machine learning can help. And the other motivating scenario is we would like to predict the yield of a chemical plant. Let's say some complex chemical reaction is happening with many large molecules. Given temperature, pressure, and amount of catalyst, we want to estimate how much yield, output product we will get with inherent uncertainty estimates and incorporating uncertain estimates in the input as well. So there are two kinds of choices for this type of task. The first kind of choice we've already learned is we restrict the class of functions we consider, such as linear combination of basis functions, or let's say neural networks with predetermined number of layers and number of neurons, right? So we know how to do this. The other seemingly drastically different choice is to, so we wanted to give some prior probability, or basically we want to consider every possible function and restrict the function set to using the prior probability. So we're being Bayesian. Okay, as generally we are from the Bishop book. And you will say, what do you mean? This sounds very abstract. So without going into, functional analysis and the theory of kernels, let's just think about this second comment in a pragmatic way. And the following two tips will help. So you say, the second bullet seems to indicate an infinite number of functions that we need to consider. Moreover, they are uncountably infinite, for those of you who know what this means. Well, that's bad. So we can rely on the parameters of the function and not think about the sheer number of uncountably infinite of functions. And these parameters can be a function itself, which is kernel function, as we will see. And the second consideration is, because we're working on function space and our input, let's say it's the real line or something like or real n-dimensional real space. So we have, again, uncountably infinite number of input points. So what do we do about that? So we basically ignore for the time being that it's a continuous space or we have infinite number of input points. We just pretend that we can enumerate a number of points and work from there. So we just pretend that we work with a very long vector all the time, as you will see in a few slides. With these two cautions in mind, let's move on. So here's the 2 slides of flashback of the material that we already know from this semester. In order to motivate something different as well. So we know from just week 6 before the break, how to convert, say, a normal regression problem in the input and feature space to a regression problem that operates in the kernel space. So kernel linear regression, so to speak. So if we, let's say, so this is on the top is the normal equation. that we've been seeing over and over again. And then the second equation is basically the prediction function for a new x, right? Plugging in the solution for the optimal weight from the normal equation. Okay, nothing new here. And to derive the kernelized version, if you remember from week 6, is we express the weights, weight vector, as basically a linear combination of the features. And we can then solve for these combination weights A on each training data, which involves the kernel function K, which are phi transpose, rather than phi transpose phi in the original version. So that's where we left in like chapter 6, right? So you may ask, oh, because this book is also particularly Bayesian, what is the Bayesian version of this? We haven't covered that. And that's why also the content of this lecture sits within section or chapter 6 in the Bishop book, right? He's told us about kernels. Now we need Bayesian kernel regression. Let's revisit chapter 3 as well, where we talked about Bayesian linear regression with isotropic prior. Say we look at the simple version, where the prior is basically the weights are mean 0 and spherical covariance. We know that, well, this is basically the definition of the regression function. Output is linear combination of the input or features plus noise with precision beta. Weights have a prior. And then what we would like to estimate is the posterior distribution of the weights given the input and also x implicitly, but that's not random, right? So the estimates look like this. And we can also then correspondingly plug in the distribution of the weights and compute the distribution of prediction functions. We talk about this because some of these basic problem formulations will be reused for today, right? So for regression problem, we basically want to, well, in the learning phase, we want to learn weights or other things and remember them as a model in other things, including kernels. And then in the prediction phase, we want to basically evaluate, like, given a new example, xn plus 1, what's its target variable, right? And if we're being Bayesian, we would like to evaluate the probability of the target variable given everything that we know. So loosely speaking. So we will be encountering this kind of expressions again today. Notice, right, so in this slide, we're being Bayesian, but we don't have kernels. Is there a kernelized version of this? And moreover, can I have both kernels and prior? All right. So succinctly, so this is how section 6.4 have motivated this. Here's the kernelized linear regression involving the kernel matrix BK as phi transpose. These are from training data. So the training here basically involves inverting the kernel matrix K plus the regularizer term. And this is the kernel vector. So it involves the test data and its kernel value with all the training points, right? And furthermore, we can express this as the prediction as a linear combination of like kernel values, right? what did we just say? We were just saying, oh, y of x equals w transpose times phi x. We've seen this. P of w, right, it was written as P of w given alpha, is basically zero mean spherical covariance. If we write y of x in matrix form, nothing changed. It's basically this expression, matrix expression. So we now claim that because this phi vector and x, or x is fixed, they're not random. The phi matrix is fixed. W is Gaussian. Therefore, y is Gaussian. So it shouldn't be too hard to convince ourselves of that, because linear combination of normal variables is normal. So therefore, we only care about its means and covariance. Well, basically, computing its mean and covariance will fully determine the distribution of y as a vector. So now let's just do that. The expectation of y is phi times E of w due to linearity of expectation, so that's 0. And the covariance of y, we just basically expand this matrix product and then take the expectation inside the random part. So this middle part basically turns into alpha minus inverse of alpha times the identity matrix. So now what do we get? We get phi transpose. So that basically gives us a kernel matrix, right? Moreover, kernel, the ijth element of the kernel matrix is, actually not phi I, but phi of xi transpose times phi of xj. So the similarity or inner product between the two feature vectors. And the distribution of y is simply zero mean and with the kernel as a covariance. Actually, I did it wrong. I missed the alpha in, so this is the correct expression. So, okay, kernel of n and m's element is this. I missed the alpha in that expression. So that's it then. So we now have a distribution of the output. So this particular version is called Noiseless in the GP book, but we don't need to worry about it yet. And we have kernels. Indeed, this three expression here, I'm just reproducing, copying the three equations from the last page exactly, is called the Gaussian process. So we're actually done learning Gaussian process pretty much. And the rest of this class, we will just visit it again to see how we use it for regression and establish some more intuitions. So a Gaussian process is defined as the probability distribution over functions y of x, such that the set of values of y of x evaluated at the arbitrary set of points jointly have a Gaussian distribution. So remembering the two tricks we were talking about in the intro slide, saying how do we do PDF over functions is hard, but we basically think about the infinite number of points as an arbitrary set of points for any given n, so a very long vector. Basically the function parameter is now implicit, right? So we're concerned about Gaussian distributions. The key parameter is the covariance matrix for a good reason. Right, so more generally, so one can define stochastic process many different ways. The way that this is defined in the GP chapter is specified by giving the joint probability distribution for any finite set. So it's basically restating the same thing, right? So we're defining a stochastic process via any finite set of values. Again, very long vectors in a consistent manner. Like what this is, we'll elaborate. A common choice is to set the mean of this function to 0. Basically, E of y is the 0 vector because we don't have knowledge that says otherwise. And because the joint distribution are Gaussian, the joint distribution of any of these vectors is fully specified by their second-order statistics. All right. In the rest of today's material, we'll see lots of visualizations with x in 1 dimensions. So this is easy to visualize. X in 2D is called a Gaussian random field. It's also called Kriging in geospatial and biostatistics. So they can be visualized, but it's a bit counterintuitive, as you will see in 2 slides. Okay, having defined the Gaussian process, and moreover, in the last slide, we were pretty much saying y as a vector is distributed according to the normal 0 vector and the kernel matrix K, right? So what is K? We know K is the inner product of the 2 feature matrices, right? The top few, these are the, like, basically from previous slides, nothing has changed. Kernel is now implicitly defined by phi of x, right? We can also explicitly define a kernel. So again, in week 6, we have these exercises or these wall of property of kernels on how to construct a kernel. And there were examples on how to convert like a set of inner products to a kernel and do it the other way around, given the kernel recover a inner product. So this is the place to use them. So we can explicitly define a kernel by writing out a function such as the Gaussian or squared exponential kernel, as the GP book calls it. We can also define not a squared, but just an exponential kernel based on the absolute distance. Because this kernel is a function, it's actually the parameter of the whole Gaussian process. And we can evaluate this function on any set of finite points, or basically on any pair of points, right? And then do this for n choose 2 pairs. So this uniquely defines the Gaussian process, right? Zero mean Gaussian process. So that's a little bit of magic, right? So here are a few types of particularly useful kernel functions. And I think in this class, we will only be concerned about these and not other more exotic ones. We can have a linear kernel when phi x is x. We can have what's called a stationary kernel, when the value of the kernel only depends on the distance, or basically the difference between the 2 vectors, 2 inputs concerned. Moreover, we could also have what's called a homogeneous kernel. Basically, the value of kernel is only depend on like the distance or how far away x and x prime is, no matter what direction the difference is. Right, so I'm not putting that slide back here, but in chapter 6, there's a whole heap of kernel construction tricks, right? The product of 2 kernels, we can add 2 kernels up, multiply them, right? Compose functions on top of kernel, they're still kernels. So here are examples. The first picture is from the Bishop book. it's taking two kernels, right? The first one is a Gaussian kernel, and sampling, I remember it was 50 points, or it wasn't. Well, basically but we say we're looking at a space of a whole uncountably infinite space of functions. So these are some samples from the function. And so the left plot is the Gaussian kernel, right? This one. And here are 5 different samples from this function space. So how do we read it, right? So if we read comparatively, the second plot is the exponential kernel. So we can see that this, the plot on the left, the function changes more slowly, right? And then, in the second plot, there are many, let me call, short-term fluctuations. The function appears very jagged. So why is that? So kernel is intuitively a similarity value between function values at the 2 input points, x and x prime, right? So the x horizontal axis is x. At any given 2 points, let's say x here and x prime here, the kernel value determines how similar, well, the correlation, right? So if we go back to Gaussian process definition, right? So k of x and x prime is the covariance between y of x1, or actually y of x and y of x prime. Right. So when the kernel value is high and positive, the 2 output values, the y values, are going to be similar. They can be both high and both low, that doesn't matter, but they should be similar. Right. And for the exponential functions, right? So actually, both of these Gaussian exponential functions, they're not long-tailed functions, meaning the kernel value basically goes through an exponential decay or square exponential decay as x and x prime gets far away from each other. Right, so the smoothness of the Gaussian kernel is controlled by this scale parameter sigma. And similarly for the covariance, for the exponential kernel, it's controlled by theta in opposite ways, because one is on the front, one is on the denominator. So we'll compare different kernel functions in a few pages. But for now, we can also look at an example of a 2-dimensional Gaussian process, right? So this is, let's say, the first dimension, x1, x2, and then the outcome is y, right? As we can see that this function is somewhat smooth, meaning the heuristic here is the function can fluctuate, but neighboring points tend to be similar. All right. So we've been staring at this expression or similar expressions that mean the same thing. So the vector of y is 0 mean and covariance determined by the kernel function or long kernel matrix for a finite number of points. You will say, then how do I go from this expression to these plots I'm looking at on the screen? So the short answer is programmatically. If we're going to write a program, we basically do a grid. All right, so let me do this in a different color. So we basically grid up the input, right? And for every point in this input, right, I sample y of x, right? And for the two-dimensional x, I grade it up. Like it's going to give me a mesh. And then on each of mesh points, there's a y value. But you say, well, okay, that sounds easy, but really how? How? They go back to multivariate Gaussian sampling, actually. The question we were asking about sampling from a Gaussian process is essentially sampling from a multivariate Gaussian, right? So given the set of x1, x2, a very long input vector, let's say xn, we're essentially sampling from a length like K is going to be a n by n matrix, right? And then we're just sampling from an n-dimensional Gaussian, which we should know how to do. In principle, given the amount of time we spend looking at Gaussian distributions, but it's still worth talking about it for GP. I forgot whether we have been super explicit about how to do this or not. But let's first talk about the intuition. So early on in this class, we've stared at different versions of this figure. Basically, in a lot of programming languages. So sampling from this, essentially spherical Gaussian is easy, right? Basically, x1, let's say, is standard normal. Your programming language will give you a routine to do this. X2 is also standard normal, independent of x1. We're done, right? What about this next one? This one is where the two coordinates, they were still uncorrelated from each other. So meaning we can now do x1 prime as in, say, alpha 1 times x1, and x2 prime alpha 2 times x2, right? Where alpha 1 and alpha 2 are, let's say, the length of covariances in each direction, right? Alpha 1, alpha 2. So that's also easy. Done. Now I take the same covariance matrix and I rotate it. That gives us essentially arbitrary Gaussian in 2 dimensions. So how do we sample from this? Oh, that should also be easy because we're doing stepwise. So now let's rotate. Right, we should be able to figure out the rotation matrix. Let's say U. Okay, it's called U because we know how to do eigenvalue or eigenvectors, eigenvalues, and U are the unitary matrix that rotates, like in PCA, that basically rotates the covariance to be diagonal. Then what we do is essentially x1, okay, double prime now, x2 double prime, being like depending on which way we're like I'm just gonna write it one way. Depending on your convention, it might be a different way. So U times, let's say, x1 prime, or actually x1 single prime and x2 single prime. Done. So that's very easy, right? So when we want to sample arbitrary multivariate Gaussian, not in 2 dimensions, but let's say in 500 dimensions, we do the same thing. Yeah, we call the standard normal sampler. We scale each axis based on the eigenvalues, and then we rotate it using the eigenvectors. Done. But this is the bottom half of the slide, right? You will say, wait, what's this bit about? So what this bit about, in essence, this is taken literally from the Gaussian process book, the appendix. And we will revisit this towards the end of the class. If you don't get it, just give it a little bit of patience. It's okay. So kernel matrix is denoted as K. And we would want to compute its Cholesky decomposition, denoted as K equals LL transpose. where L is the lower triangular matrix, and with its diagonal values also positive, right? We'll talk about Y in a sec. Right. So then what you do is we generate essentially a like this, essentially this random run Gaussian samples from zero mean univariance. And then we compute x equals to m mean plus L times U. We can then verify that the variance of x is k, because it's essentially, well, L transpose. The standard Gaussian in the middle vanishes because its covariance is I, is the identity matrix, right? So this seems to be correct. But what happened, right? Between the intuitive version we talked about, which requires two steps. We first do scaling, then rotation. In here, we just deal with this L matrix. And it's still correct. And why do we want to be doing this rather than the eigenvalue eigenvectors? And there is also a practical trick, right? In practice, it may be necessary to add a epsilon I to the covariance matrix so that we make sure that this is well conditioned, it's not nearly singular, and so on. So the reason why we do Cholesky decomposition is it's not exactly written up in either of the textbooks, but we have the internet, right? So if you look up Stack Exchange, there is a nice summary. The argument, the core argument is actually it's faster to compute. And the argument of why it's faster to compute is not at the, like, the order of computation is not different. So basically, both so eigenvalues and inverting a matrix are both O n cubed, shows Cholesky. But the key difference here is the constant in front of the n cubes. That makes a difference. Right, so this is a table pretty much compiled from Gingallo, information from Gingallo's book. It's from another book. Right, so Cholesky factorization is n cubed over 3. If we do spectral decomposition, basically solve for the eigenvalues and vectors and so on, if we want the rotation matrix, it is 9 times n cubed. If we only want the diagonals, then it's 4 over 3 of n cubed. So between 9 times n cubed and n cubed over 3, it's 27 times speed up. It's still more than an order of magnitude, despite the scaling with respect to n is both cubic. As you could possibly appreciate, which is, I won't ask you in the exam, but basically there is lots of hard work that goes into making numerical algorithms, linear algebra fast, and do it properly. For the purpose of this class, we can assume we just use these results. Yep. Okay, so that's basically how we define a Gaussian process and how we define kernel functions, and how do we basically examine the type of functions defined by a kernel. Is there any questions so far? No? People are all happy? Okay, since we've been just talking about Gaussians, we'll move on and talk about regression. So as per tradition of the Bishop book, right. Okay, there is one question. Let me read that. Right, Qinyu asks, oh, right, so yes, isn't the kernel regression we did in week 6 already Bayesian? It's why are we doing this again? That's a good question. Let me go back a little bit and try and clarify this. Right, so you're talking about this slide. In here, we have a y value. So the difference between so-called Bayesian version and non-Bayesian version in this particular class, or according to the Bishop book, is so this is what we call point estimate of y. We don't have probability of y or posterior probability. We like, okay, the Bayesian view desires the posterior probability of y, a new y, given all the training data. Let's say we denote it consistently. Let's say a new y, given all the training data x and plus 1, the new test data x1 through n, y1 through n, and so on and so forth, and maybe other things. Just leave that. I hope that makes some sense. And we want to express this with kernels, not with the phi. So you can say the same thing about the next slide, saying, oh, we want the k in here. We don't want the phi vector and phi matrix. That's basically the goal. If you refer to the GP book, so basically, let me say that the GP book, I think either, right, maybe 2.1, has what's called the wave space view of Gaussian processes, which are essentially trying to directly derive Gaussian process based on Bayesian linear regression. It's possible. Yeah, I choose not to cover it because so the trade-off between the wave space view is that the derivation looks a bit long. The functional space view, as in GP book calls it, or the way that the Bishop book does it, is that the derivation looks simple. As long as we wrap our head around the concept that, oh, when we talk about functions, we think about it as values of y over a very long vector. Okay, Vikram asked, I'm still a bit stuck about how to understand a Gaussian process. What is the relation to a stochastic process? Good question, actually. Right, so I see the purpose of this particular lecture as going through Gaussian process 3-4 different ways until we kind of get it. If not, we come back again next week and get it. Because the functional, like when we talk about space of functions, it is scary and it can take a bit of time to get. So to answer Vikram's question, maybe let's just get through more examples in the regression sense, and then we come back to it. Shall we do that? Okay, thanks. Right, so this is, for example, different from stochastic processes that some of your math and stats majors might have seen somewhere else, which is to say, like, for example, my group work on prompt processes, which we talk about a random function as the intensity function that generates points in real time. We could also just talk about, yeah, so stochastic, so, okay, here's a short version that encodes intuitions. If you have known stochastic process as basically, we have a function y of t, usually like, okay, stochastic process. In a lot of textbooks, it's defined over time. Let's just say that. So a stochastic process is basically a time series, but probabilistic, right? So in every point in time, the output has a distribution. That's a stochastic process. If you think of it as that, then this y of x as stochastic process is not too different, right? So in the pictures, so for every x value, we have a y, and they are random. The trick is they're not only random, but y's of different x values, they are correlated with each other. They depend on each other. So therefore, we need to do this multivariate Gaussian sampling business, and cannot say, well, given history, we can say given history, what's the distribution of the next y of t, but that's not the complete picture, right? So I hope that helps a bit. Right, Hao Yang says, why the GP is sampled using decomposition matrix of a covariance matrix. Again, good question about this bit of material. Another, I guess, confession is in the last while, I think for a few years, I've been using this sampling multivariate Gaussian, but not Gaussian process question to interview PhD candidates in my lab. Most of people don't get it, which says that sampling a multivariate Gaussian is not a widely known concept, I would say, or a technique. But now I know if I use it in this class, everybody will get it. Anyway, so yeah, ending the aside, I argue that if you don't do the decomposition, so again, this is how sampling works. We can treat, for example, sampling of random variables as a black box, and we just use it. For example, we could go one level down. Actually, we will have a sampling lecture, which will start by talking about how to build a standard normal sampler. So yeah, so in NumPy you have this, and you can also in NumPy you can have the multivariate normal. What we're doing is to talk about what happens under the hood in the multivariate normal sampler. We will need it because in Gaussian process regression, we are better off knowing it, as we'll see towards the end of the lecture. Yes, correct. Hao Yang said, yes, sampling in 1D, you just essentially call this function np random dot standard normal, or in some other program languages, it's called random.rand, rand-n, right? But for multivariate, we're talking about how to decorrelate essentially the different dimensions with the full covariance matrix and go back to use the standard normal sampler for it. I hope that helps. If not, we'll talk about it again when we encounter the Scholastic algorithm towards the end. And shout at me or leave a note in the chat. Okay, there we go. Gaussian process regression. This expression on the top is what we've been looking at so far. I would say this is called noiseless version of GP. Oh, we have a kernel function, we have outputs. Now we add some noise. As per convention of the Bishop book, whenever we do the regression, we have an expression like this, where there's a y plus some random noise gives us output t, right? Moreover, we know the distribution of the random noise. It's basically zero mean and with precision beta. Or okay, nothing new. And we can, if we have n of these y's and t's, we can just write them in matrix format. That's also nothing new. right, because the noise are uncorrelated, the precision matrix is simply beta minus 1 times identity. Now, the new thing in this slide is basically to put these two equations together, P of t given y as a vector and P of y as a vector, and derive what is the distribution of t, right? So the claim here is y plus some independent noise, some IID noise, still leads to a Gaussian distribution, which is still zero mean. I think we can convince ourselves of that pretty easily. So y is zero mean, and then E of any of these like noise things is zero mean. So that's still zero mean. And the covariance, yeah, I wouldn't derive it here, but it should not be too hard to do so. Basically put these two Gaussians together, integrate y out. Then we get the covariance matrix, which is essentially a combination of the kernel matrix plus this noise term, where the noise term is only at the diagonal. Right, so we basically have something like k11 plus beta minus 1, k12, k21, and so on and so forth, until we get kn plus the same noise. Right. So C is roughly looking like that. As we there was a side remark in the sampling slide saying that it's actually good to do this to k anyway, to keep like the inverse of k or the Cholesky of k stable. So in this case, noise might be numerically a good thing. All right. So that's definition of Gaussian process regression. Now let's look at, well, if we do regression with a kernel and we explicitly define a kernel, right, what does it mean, right? So the implication here is the training in Gaussian process regression is implicit. It's done via the matrix C, which include the kernel function. This is actually the same argument we were making in the kernels week. Before the break, I know it's been 2-3 weeks and it's expecting most people have forgotten about it. So in here, training, we're just computing C, right? So this is training. And essentially training C requires remembering like more than n pieces of information. Right, we haven't talked about prediction yet because one of like Qin question was like, oh, what's Bayesian about this thing? And our answer is that's about prediction, but that will come. So right now, let's just say we define a relatively complicated kernel. In the previous example, we were just looking at the Gaussian and exponential. And now we have basically, this is the like square exponential. What happened? Okay. Squared exponential component. And then we have a constant. And then we also have a linear component, right? So these are 3-component kernel with 4 parameters. So we vary these 4 parameters and we see what the resulting sample looks like. So these, I think we should covariance function of 6.63. All right. So we first right. The first thing that got varied is, for example, theta 0, right? With the for the first 2 diagrams, everything else is the same. and the functions kind of look similar from these two samples. That means theta 0, the scaling factor in front of the square exponential doesn't have too much of an effect, with everything else held the same, right? So another key thing to notice is that theta 1 is 4. So that means the Gaussian has a nice bump and tapers off. So the fact that theta 0 is not too important means that once the Gaussian tapers off, what the constant in front of it is not very important anymore. So if we can mentally convert, for example, theta 1 to the intuitive notion of variance in a Gaussian distribution, right? So it roughly corresponds to, right, well, like 1 over theta 1 square root correspond to the notion of like sigma squares or the standard deviation. In that sense, if theta 1 is 4, then the standard deviation is about 0.5, meaning 3 standard deviation out things are pretty much unrelated. But this pretty plot is from like -1 to 1, so that's more than 3 standard deviations out, right? And then moving on, comparing the first plot here and also the third plot here, everything else is the same. Now what's different is this 64. That means like, okay, standard deviation, or basically the scale of the variance. I shouldn't say standard deviation because it's not a distribution, but basically the scale parameter, shall I say, decreased, right? The multiplier increased, but the length scale of the same variation decreased by a lot. So therefore, this function is changing. This function is changing a lot faster than the first one, right? This one. Okay, yeah, change faster. Now moving on. Oh, right. So from this one to this one, again, the scale parameter is different. It decreased by 16 times rather than increased by 16 times. So this changes slower. Changed a lot slower. What about the other ones, right? You might say. So between this first one and the fifth plot, what was different is this theta 2 is the constant, right? So if the constant is high, then the similarity function k, right, is high. That means any 2 points are a lot more similar or a lot more correlated, should I say, because these are jointly Gaussian, than otherwise, right? So I would just, correlation is high overall. After all, these are all zero mean Gaussians, meaning that remember that the mean of y, right? Okay, y, I'm just gonna, y, oh, this is, I'm not actually sure if this, this particular plot is plotting t or y, but like y is zero mean Gaussian with kernel k, right? So what this plot shows that the overall mean of y is 0, right? So this is e of y is here. Basically the variation across the curve is low, but the curve itself can basically sit above 0 or below 0 quite a lot. That's how we read this fifth plot. And the sixth plot is this last term, which is the linear correlation strength. What does that do, right? So if a linear correlation, well, it imposes the similar effect, right? Where if both of the x's are small, right? So for x's that are close to 0, they almost have no effect, right? One way to read this is that for x close to 0, this area is similar to this area, right? So this plot must have been produced with the same random seed. This is another trick in doing your machine learning simulations. But the outer areas, when the absolute values of x are big, they become dissimilar, right? Moreover, when one side of it is like, notice that these x's, they have opposite signs, right? So that means for the left and right hand side, when one side is big, the other side tend to be small. And the correlation, because the correlation is driven to be negative. All right, that's okay. I hope that explains a little more of the intuition behind GPs. Now we're ready to dive into the prediction function, or basically the goal of regression is to be able to estimate or interpolate essentially and extrapolate new values and not just remember the n data points we have observed. So here we go. We have, again, target T with a noise term. And from the last pages, we know that P of T, right? Tn as a vector is 0 mean. Write this again. It's roughly 0 mean and with covariance matrix C. And right now I have a subscript of n, denoting that it's from the training data. Yeah, in order to think about test data or prediction, we can simply first look at the joint distribution of the training and test points because they are Gaussian. If we simply change the subscript and pretend now we have the test point as part of the training, we can just plug in this equation right here and write this, right? So the joint distribution of the n+1 t variables as a big long vector is the same thing, 0 mean and Cn+1. The only trick is to figure out what's inside Cn+1 because we have not encountered it, right? C of n is k plus the like beta minus 1i, right? So we know that. And the vector k basically is the kernel value of test point xn+1 with respect to all the other training points, right? So which is set here, vector k has elements like ranging of like every training point with respect to the test point. And k transpose is the same. And then the C constant on the lower right-hand side, it's not hard to imagine it's just the kernel value of the test point with itself plus this noise variance term. All right. So that's all good. We just figured out the joint distribution of all t plus like n+1 targets. Now we need to apply the trick we know from before, again from chapter 2, conditional Gaussians. Basically, if we condition this joint Gaussian, multivariate joint Gaussian distribution on the first n+1 dimensions, what is the conditional distribution of the new dimension, right? So if we plug in, again, no derivations here. So if we simply apply this conditional mean and covariance formula recipe here, yeah, we know this thing is jointly Gaussian, so therefore conditional distributions are also Gaussian. We can simply compute the conditional mean and variance of t plus n+1 given the first n's expressed as a function of x. So the input matters, right? We're doing regression. So the mean, the notation here in the Bishop book can be a little bit counterintuitive depending on how you're thinking about it, right? So the interpretation should be the conditional mean of Tn plus 1 as a function of xn plus 1. It is not the mean of xn plus 1. Xn plus 1 is input, it's not random. Right. Right, there we go. So the conditional mean is K transpose inverse of the covariance with noise, C n minus 1 times T. Right, so if we were to separate the two parts, right, so this part we could call training. Similar to training in kernel machines, the training involved here is to compute the kernel, invert it, and multiply it with the training output, right? And this part is this other part. So it has the test. It's basically the kernel value of the test data with the training input or training input. Okay, test input with respect to the training input. Okay, that seemed to make some sense. Similarly, the covariance or variance of this 1D output vector is C, small c, which is the prior variance of the input, subtracting this whole part of the training variance, right? So the way we can read this is this, can read this part as variance reduction due to having the training data. I'm going to call it quote unquote training because, right. Meaning if there is no no training input, then the, like, if we're going against the Cn plus 1 matrix, the prior variance of Tn plus 1 on itself is this C term. Now it has been reduced by conditioning on the first T n dimensions. So one thing to remember or useful thing to know is for multivariate Gaussians and many, and in fact any other distribution, joint distribution, conditioning on something always reduces or doesn't change the uncertainty or doesn't change the variance, right? So conditioning cannot increase the variance. Once I know part of the variable, I cannot like increase my uncertainty, which is one nice thing. All right. So the book also has a nice interpretation in the following way, right? So which is a restating what we were scribbling in this area. So it says that the mean function of Tn plus 1 can be interpreted as a linear combination of kernel values between the training points and the test point. So this is quite like SVM, right? Despite the alpha n or ANs are not sparse, right? And then AN is basically computed from Cn minus 1 times T. So yes, you were seeing SVMs in disguise with different properties and Bayesian. I hope that makes some sense. None of these derivations are particularly new. You're expected to remember or being able to make sense out of 6.66 and 67, for example, but hopefully that's not too much of a tall call. Nothing is closed book in this class. You can always look it up. As long as you can understand it and apply it correctly, I think that's good enough. Whether you go through the exercise to actually plugging in 2.81 to get to that, that's your decision. All right, here we go. let's look at a few examples. We've pretty much done covering the GP regression material. Now let's just look at it, as I said, left and right and front and back, and try and establish some of our intuitions. So here are just Gaussian process with one training point and one test point. And furthermore, this particular thing graph is drawn on, like just not the input space, but just the output space, right? So let's say P of what this expression that we saw from last page says is essentially T1 plus NT2 is distributed according to normal, the simplifying notation of two zeros. Therefore, this Gaussian is centered on 0. And the covariance matrix looks like, okay, kernel of, I'm going to call it kernel 1, basically that stands for kernel of T1 and T1, right? And then kernel of 2, 2. And then this is kernel of 1, 2, the same value because it's symmetric. Okay. And what does this figure say in the Bishop book is we now want to obtain P of T2 given T1 because T1 is the training point and T2 is the test point. So therefore we fix a T1. So T1 is here. T1 value is here. And what happens to this two-dimensional Gaussian is that we essentially using this blue line to slice the two-dimensional Gaussian probability mountain open. And the conditional distribution is, if we envision this as a Gaussian mountain, it's the cross-section of that Gaussian mountain. What that means is that the mean of this Gaussian mountain, well, these are Gaussian mountains, therefore it's symmetric, right? The mean is in the middle, it's here. So this is called the mean of, the mean of T2, mean of T2 given T1, right? As a function of x2, x is not drawn on this slide. And then the variance, the covariance, right? So this Gaussian is roughly spread out because it's, right, so the uncertainty sort of bracket goes from there to there, right? More or less. We also made a claim on the last slide that conditioning like this reduces uncertainty. This can be seen by basically this, let's say 1 sigma or 2 sigma bracket is smaller than the otherwise sort of the larger bracket from all the way to the top to all the way to the bottom. We actually saw exactly the same figure in chapter 2 when we talk about conditioning and slicing open two-dimensional Gaussians. This is an application of it in GP. All right. I would say this picture is important to understand the intuition, but it's not one of the most oftenly seen GP visualizations, which we'll move on next. So before we do that, unfortunately, the Bishop book didn't have a lot of the other often seen GP visualizations. We're going to move on to the GP book. One thing we have not done in this SML class is to expose people to different notation systems, which can be like a real exercise. So therefore, based on necessity, we're doing it now. And this is basically a table that summarizes the different notations between the Bishop and the GP book. So in Bishop, we have y equals phi times w and x and phi of x. In the GP book, we still have phi of x, that's the same. There is a difference between small x, which are vectors, and big X, which are matrices. The y in Bishop book is called f. And the target with noise is now called y. So that's a slightly confusing thing because t in Bishop book is called y. And then the test data point is called xn plus 1 in the Bishop book. They're called x stars. All right. And moreover, the noiseless version is called f stars now. The noise covariance is called sigma n squared in GP book, and it's called beta inverse in the Bishop book. Similarly, the mean function of the test data point is called basically f star bar, corresponding to the mean, and then variance is called v of f star. All right, I know it's confusing, but hopefully having this table helps us comprehend figures like this. So I would say this is some of the common formats of Gaussian process plots that you'll encounter elsewhere. So in GP book figure 2.2, right, panel A is what we have seen. If we just have a GP prior, like a kernel function with no given points, we draw 3 function instances, we get this, right? The dots indicate that the value of y that are actually generated, right? So for the blue line, what we do is grid it up and then generate the y. As you can see in the areas where y changes fast, it looks sparser, right? And in 2 other functions, we just connect the points. So this is precisely speaking not exactly like sampling over a continuous function space, but you can also see why we just say, well, treat it like a very long vector because this is how we operate anyway in practice, right? And then because we know that y's tend to be continuous, like connecting them is not exactly wrong. It does convey the right intuition, despite it's not analytically super correct, right? So if they're drawn as lines by joining a large number of evaluated points. Okay, then what's panel B? It's so this is the noiseless regression case where, well, we simply set the noise variance to 0. And then if we know we know 5 points, right? 1, 2, 3, 4, 5. Given 5 x and y pairs, now that they're not random, so the prior condition on 5 noise-free observation points. The shaded area represents the pointwise mean, basically, right? This mean function. So it's a mean function it's a mean as a function of x. Now you can see why this notation m of x plus 1 makes sense. So basically xn plus 1. So these grid points are all the xn plus 1s. When we change it, the mean changes. And therefore we connect them and make it look like a function, right? And what we do is draw the mean plus and minus 2 times the standard deviation for each input value. This, as a reminder, plus minus 2 standard deviation correspond to essentially 95% of the probability mass. It's also called the 95% confidence interval, right? What's worth noticing from this plot is, okay, variance at the given points is 0, right? Shrinks to 0 because we know these points. And then in here, the variance or confidence interval increases, right? Because we're extrapolating rather than interpolating. When we're interpolating, the variance sort of grows a bit and then shrinks towards the next point. But there is no more point towards the left, therefore the variance increases. All right, so I hope that helps. This is for you to parse afterwards. So basically, this is the posterior distribution, right? So this is the C term. So noiseless. So this will be the little c, and then this term is this. Using our like notation mapping, right? So can k vector, k matrix inverse plus k, and k vector again. All right. So let's move on. Here's another picture illustrating the concept, right? So panel, this one we have seen. So this is identical to the one we just saw of a Gaussian process conditioned on 5 points with the varying variance, right? I would say, so this kind of plot you will see a lot in Gaussian process literature. It's also for us to say that in Gaussian process, it's easy to draw functions in 1D. Beyond 1D, it's like, can you imagine a landscape with like shaded confidence interval in them? That's just a visualization nightmare. Don't do it. And don't torture your readers, right? So in the next function, the next panel shows the posterior covariance between f of x, like basically any of these red, blue, and green functions, and f of x prime for the same data in 3 values of x prime. Right. So there's several observations. So these are covariance functions, right? So k of essentially we call k of x prime, right? And moreover, the colors in the right-hand side plot does not correspond to the colors in the left-hand side plot, because the left-hand side plot is governed by the same C or conditional C, like x conditional xn. Right. What this means is, for example, in the blue covariance function, the input x prime, so x prime is here. It corresponds to the peak of the covariance function. And then it shrinks to 0 at the given points, right, at the training points. So there's a training point here. How do I indicate it? So it's plus, huh? Training point here, training point here, and here, and here. So in all of the training points, the covariance is 0 because the training point itself is not variable, fixed. Increases while it's at its peak at the x prime values, right? So peaks here. The one potentially sort of confusing thing or a conceptual understanding, which I argue is useful to have, is that right, so the covariance can become negative, right, in these points, right? Why is that, even these points? So they become negative because if the smooth function happen to be less than the mean on one side of the data point, it tends to exceed the mean on the other side. Meaning the function, when the function is smooth, it tends to, when it's decreasing, it decreases. When it increases. So therefore, the correlation between like points on either side of the mean crossing point are negative. So causing the reversal of the sign of the covariance at the data points. Right, the prior covariance is simply the Gaussian shape and never negative. This is also to say, right, so Gaussian process is a very rich representation of the covariance, right? So despite the prior covariance function is, let's say, square exponential, the actual covariance matrix on the set of points, it can be anything, like it can have negative values. Okay, there we go. Here is basically 2 of the plots that we saw combined. The first plot was right, sampling with different kernels, right? So in this plot, what we should see is sampling with varying kernel parameters. The second idea that's encoded in this particular plot is, right, these are showing posterior distribution with a set of given points. With, let me say, better worded, given input data. And we're going to build upon what we saw in these respective cases. We know that for example, in this, and the parameters are done up here, meaning sigma n, we can interpret this as noise variance, sigma n squared, right? So for this one, noise is very low. And it behaves, there's a whole heap of training points that are like denoted by crosses here, right? So in this B plot, the noise is very low. It goes back to basically this plot we saw on the last page, where the noise is clipped to nearly zero at the training points. And the function sort of tries to pass all the training points. And this is what's happening here. So the noise shrinks to zero and blows up at the outer edge, right? But then in between training points, it sort of grows and then shrinks back. Right, and then these other two parameters, L is the scale / length. It's put in the denominator, so it's the inverse of the other parameter we saw a few slides earlier on, but it's 1 anyway. And then sigma square f is the strength of the RBF. Right, so what has changed between, let's say, the first one? The first one, the strength of RBF is 1. And the less, right, so between the A and B, noise level definitely changed. And then the overall scaling in front of the square exponential also changed. So for example, B is smoother, well, A is smoother than B because B has less of a multiplicative factor. Right, in C, this is interesting, because now the noise is very high compared to the other two. What that means is that the Gaussian process function does not try less hard to pass through all the training points. And overall, it's more smooth, right? And furthermore, when we evaluate the posterior, like the variance never shrinks to zero. This concept is also illustrated in a Bishop book. In this, I would say the Bishop book sort of skips the intermediate plots and then just directly go to this. It can be less, like, not super intuitive. So this data set is what the Bishop book keep using, a sinusoid between 0 and 1. And then it fits a Gaussian process with noise. With a couple of given points. This is what the pink band is the covariance as a function of x, and the red line is the mean function as a function of x. So hopefully this plot and the plot C in the last page reinforces each other. If not, this is something to look at after the lecture or ask me questions. So now let's get to the algorithm that we promised you and which you will be responsible for in assignment 2. So the central question we would like to address is how to implement this two equations. that keep appearing, the mean of x and the covariance of x for for prediction. So you realize this is a slightly different question than when we talk about sampling Gaussian process just from the prior, which is just a multivariate Gaussian sampler. In here, we're no longer talking about multivariate Gaussian because we evaluate this function like sort of individually for each test point. But some of the computation are nonetheless similar. So this algorithm is taken from the GP book. So let's walk through it, right? So here we go. K plus noise times I is simply Cn in the Bishop book, right? And we would like to, so it is the covariance matrix of all of the training output, right? Given that we know how multivariate Gaussian samplers work, that intuition says if we have multivariate covariance matrix, do the Cholesky decomposition like this, right? So that's what we did. The first line says Cholesky decompose this Cn. And we also kind of argue that you want to do this instead of doing the inverse or eigenvalues, which are about like roughly the same complexity, right? So let's do that. We want the inverse of Cn in these expressions, so therefore do the Cholesky. The next line needs unpacking a little. So what we're after is, let's say we would like to solve, let's say, the equation inverse A of B for a square matrix A, right? Which is exactly what we're trying to do here. So in here is Cn minus 1 times T, right? In order to do this, in linear algebra or NumPy is the backslash operator, but there's lots of computation that goes behind the backslash. Here's the under the hood, right? So in order to do this with the Cholesky decomposition, what we do is we first Cholesky decompose A or Cn, and then we compute this backslash twice using L rather than computing this backslash once using the original Cn, right? So what you do is first solve Ly times equals B, and then solve L transpose X equals Y. So that corresponds to doing the backslash twice. So that's that. Once we have this, right, this alpha vector outlined in the algorithm, we essentially have like C inverse of Cn times T. We can then apply it, right? So, line 4 basically computes the mean as a function of input, where K star is evaluated for each input. And then the variance again is right, L back, right. So the V vector is L backslash K star, and the variance is basically the self-variance of the input point minus the variance V vector transpose itself, or the inner product, the norm of the V vector. How do we think about the V vector? It's basically right. So we're solving right. LV equals K star, right? And that is the V vector there. And then simply verify V transpose V is K transpose Cn inverse of Cn times K. Okay, once we know this, so this is the mean function in this line, and then the covariance function in line 6. And the bonus in here is to evaluate the log likelihood. So in the GP book, Y is the target, or T, in Bishop book. So the log likelihood of Y given the input is simply basically that constant, or normalizing constant in front of Gaussians, and then log of the Cholesky factor plus the Y times alpha, right? So this is the Gaussian likelihood expanded in terms of the Cholesky factor. What is worth noting is that the log determinant, right? So the middle term, where does that? Right. So this one, it's the, remember in multivariate Gaussians, there's a determinant term that sits under in the denominator of the Gaussian. Computing this, you're better off using the log trick, right? Because this could have numerical blow-ups if you're just multiplying lots of very small, very big eigen, or like they're essentially eigenvalues, right? All right. So that's the algorithm. So what kind of computational cost are we talking about? So computing the inverse of C, as we walk through, is order of n cubed. And then on top of that, we compute this backslash a matrix multiply, that's n squared. Compared to linear regression or Bayesian linear regression, so that compute time is cubic in terms of the number of features. So which one is worse depending on your application, whether m is bigger or n is bigger, and everything, and what you want to get out of it, right? So, and similarly, it's m squared for each time test point. So that's okay. That's pretty much all the technical content today. Let's talk about this robotic arm application, which, yeah, I discussed this material with other colleagues. They were like, this is not the best GP application, but right, so but it does make sense, right? So the setting is as follows. There are 21-dimensional input, 7-dimensional output. So they are using square exponential covariance function. They estimate separate length scales for each input dimension, sigma f and sigma n squared. And then the estimation of these length scales are done using marginal likelihood, which is in the next slide, but you're not responsible for, on a subset of data using holdout data, right? So we talk about training is basically computing the covariance and then remembering it. So we can use holdout data to essentially use marginal likelihood to estimate these hyperparameters, which is nice because as those of you who have been taking other applied machine learning classes, like searching over hyperparameters is just, yeah, it's a lot of times it's a black art. In this assignment 2, you will see one principled method for doing it using GPs. All right. So there are about 49,000 input-output pairs. 5,000 is for testing, the rest for training and validation. And there are 2 evaluation metrics. So the selling point in the GP book says, look, right, GP sort of outperforms the other methods by a lot in terms of both metrics. And these are with approximations because now we can imagine, right? So inverting like this roughly involves inverting or computing the Cholesky of a 40,000 by 40,000 matrix, which is what 1.6 billion elements. Yeah, it's hard to do this brute force even with the modern hardware. So there's lots of literature on approximating Gaussian process for large problems, which we won't get to. So, and just in a nutshell, this is how you roughly do like hyperparameter estimation. So 6.61 is what we saw before, nothing new. And this line is the like multivariate Gaussian likelihood. No, this is the log determinant term we talked about, using the sum of logs to compute. And then we can essentially differentiate this using some matrix constants with matrix expressions. We can differentiate against any parameter theta I involving the covariance matrix. So the hard part of evaluating this is these, right? As with the cheap gradient principle, evaluating this is not a whole lot harder than like computing the original problem. So for example, in the algorithm that we covered in the GP book, these are already computed. We just compute and store them, and then gradient descent, for example, over theta. So that's all for today. It did take a while for us to go through, but I hope Gaussian process is starting to make some sense. I know we looked at it left and right in many different ways. It is, in my mind, a beautiful way of expressing flexible functions building on the basic concept of multivariate Gaussians. I feel it's also a very nice connecting point among the concepts that we talked about, meaning linear regression, kernel-less linear regression, Bayesian linear regression. It will also be a jump point for us to talk about approximations and approximate inference in machine learning, which we'll touch upon next week and then come back again in week 11 or so. Any questions? People are happy. Okay, sure. If people are all happy, enjoying doing your quiz. And I'll see you next Wednesday after another long weekend.